Hello, welcome to Basics of Finite Element Analysis Part 2. This is the third week of this particular MOOC course, and in this week we will be focusing in detail on something called numerical integration. So, what we know is that when we are doing finite element analysis for any problem, that is when we are trying to solve any differential equation using finite element analysis, then we get several matrix terms, and the computation of these matrix terms involves integration of some functions. Now, since we use computers to do all this integration, we should have some numerical based approaches to perform those integrations. So, those type of integrations which use numerical based approaches are known as numerical integration schemes, or they are also known as, so they are known as numerical integration schemes, or they are also known as numerical quadrature. So, both of these are same. They mean the same thing, numerical quadrature or numerical integration. They essentially imply the same idea, where a function, so let us say this is x and this is some function f x, and what I am trying to integrate is this function over the domain x a to x b. Okay. So, analytically if I know this function x, let us say f x is equal to x square plus 3 x, then analytically I can integrate it using standard integration methods, or if I have to do numerical integration, then there are several ways to perform this numerical integration. So, let us look at an example. So, suppose I say that there is an integral I, and that is an integral of some function f of x dx, and I am integrating it in the limits x a to x b. Okay. Now, when we do finite element analysis, a lot of times this f x is represented as f I psi I of x, right, and here f I is the value of f x at ith node. So, suppose I have an element and let us say it has a lot of nodes. So, this f x is sum of different f I times psi I. So, I am doing I equals 1 to let us say n, then I, so this is node 1, node 2, node 3, and if this is a very long element, then maybe this is node n, no, not node n, this is node I, and this is node n. So, value of f x at ith node is f I, and psi I of x is what? The interpolation function for f of x, and this is the ith interpolation function. It is ith interpolation function for f x, and it tells how this function. So, all these interpolation functions, when you add them up together, it tells how f of x is varying across the length of the element. That is what it means. And n or lowercase n is the degree of interpolation function. So, if it is a linear function, then I will have two psi's, right. It will be psi 1 and psi 2. If I have a quadratic function, then there will be three psi's, psi 1, psi 2, psi 3, and so on and so forth. Now, please note that this thing is approximation. Excuse me. This is so actually the arrow should not be pointed here. This is approximation, and this one is exact. Fx is exact, and Fi, psi I, we are approximating it. That is why we call them approximation functions. So, mathematically speaking, if I am strict about it, this is not an equal to sign, but rather it is approximately equal to Fi times psi I. So, this is important to understand that the right side represents approximate function which may be very close to Fx, but the aim is to be as close as to Fx. That is how, that is the basic idea. So, if I have to do numerical integration, what do? I plug, so let us call this equation A, let us call this equation B, I plug B into A, this is the first step. So, then I is equal to xa to xb, and instead of fx I am putting its approximate function, and that is fi psi I of x dx, and this is summed over I is equal to 1 to n. So, let us take a specific case in this context. So, suppose this is x, and on the y axis I am plotting fx, and let us say the function is varying like this. So, my aim is to, so this is the exact function. This is the exact function which is f of x, and my aim is to integrate this function over the domain, right. Now, in reality over the element I do not know how the variable is changing. Now, this may be some theoretical case, but in reality when I am solving for a finite element problem, I do not know how this function actually varies over the domain. So, I really do not know how this is varying. So, I have to guess, I have to make some guesses, and I can guess, first guess I can make is that the function varies linearly over the domain. So, this is what? This is the approximate, this is the approximation of fx, this is the approximation of fx. So, if the exact value of this integral is all the area below the blue curve, and the approximate value of the integral is all the area below the red curve, which is a straight line. So, the approximate area is all the area below the red line, exact area is all the area below the blue line or purple line. Now, here I have assumed that the variation is linear. So, in this case n is equal to 2, right, and so this means that I have two approximation functions. The first approximation function is psi 1 of x, which is associated with first node, this is node 1 and this is node 2, then this is equal to, so actually this is x a corresponds to node 1 and x b corresponds to node 2. Okay. So, corresponding to node 1 the approximation function is, and we have seen this in this course as well as in part 1, is x b minus x divided by h, and x 2 is equal to x minus x a divided by h. A very unique characteristic of these approximation functions is that the maximum value, they have three important characteristics. The maximum value is 1, right. The second important characteristic is that associated with ith node. So, if there is an approximation function associated with ith node, then its value will be 1 at ith node and it will be 0 at all other nodes. So, psi 1 is associated with node 1, psi 1 is associated with node 1, and that is why when I put x is equal to x a, its value comes as 1, because x b minus x a, I am defining it as h, which is the length of the element. So, its value is 1 at node 1 and at node 2 its value is 0. Similarly, for x 2 its value is 1 at node 2, but 0 at node 1. Now, the approximate area is equal to area of this trapezoid, right. So, what is this? Is the area of this trapezoid. This is a trapezoid and that is the approximate area, and that area equals f1 plus f2 divided by 2 times h, right. It is f1 plus f2 divided by h, where f1, this is f1 and this is f2, and earlier we had also defined that fi is the value of fx at ith node. So, f1 means the value of function at node 1, f2 is value of function at node 2. So, this is the trapezoidal rule. This is one example of a numerical integration scheme. This is one example. So, let us call this equation C. I can also have a case where n is equal to 3. In that case, the element length will be still same. Its first point will be x a, second point will be x b, and there will be a node at midpoint, and here the coordinate of this will be x a plus x b divided by 2. So, let us say, so if it is n is equal to 3, then it is a what kind of interpolation function? It is a quadratic interpolation function. So, I am just going to plot some quadratic function. So, it is some quadratic function. So, this green curve is for n is equal to 2, It is for n is equal to 2, and it looks very close to a straight line, but let us say that it has some curvature. So, the midpoint is this is the midpoint, and its x axis coordinates are xa plus xb over 2, and on the y axis the value of function is f mid. I will call it f mid. Then if I have to find this area under the green curve, there is another rule known as Simpsons rule. So if we had 2 points, then we use the trapezoidal rule to find the area under the curve. If the function is quadratic in nature, then there is another formula known as Simpsons rule, and we use that to find the area under the green curve. And for that, the area is, so it is again approximate area, and that approximate area is equal to area under green curve, and that is equal to h by 2 into f1 plus 4 f mid plus f2. Okay. That is the, so this comes from Simpsons rule. This comes from Simpsons rule. So to find the area under the green curve, we have to know the 3 values of the function. The first value of the function which we have to know is f1, the second value of the function we have to know is f mid, and the third one is f2. Kitna time hai? F mid. So this is important to understand. We have to know 3 values of these things. So what we will do is we will recap. So from trapezoidal rule, my approximate integral was h by 2 into f1 plus f2. Okay. From Simpsons rule, the integral was h by 2 into f1 plus 4 f2 plus f3. I have just renumbered some of these indices, so I will make it explicit. In these 2 equations, f1 is for f of xa, okay. f2 is equal to f of xa plus xb by 2. So this is the midpoint. f3 is f at xb. These definitions are a little bit different than this definition, because here f2 means the last point, but in these things f2 means the midpoint. So that is the only difference. I can rewrite this trapezoidal rule. I can rewrite this trapezoidal rule in another form. I can write it as f1 times h by 2 plus f2 times h by 2. It's the same thing. Similarly, the Simpsons rules can be written as f1 times h by 2 plus f2 times 4h by, actually I am sorry, this should not be h by 2, it should be h by 6. So 4h by 6, and there is a 6 here also, plus f3 times h by 6. So it should be 6 here also. So what we are seeing here is that the integral is nothing but a sum of the values of the function at specific nodes times a constant. This constant is h by 2 and h by 2 in trapezoidal rule. And in Simpsons rule, this constant is h by 6 associated with f1, it is 4h by 6 associated with f2, and it is again h by 6 associated with f3. Okay. So these encircled constants, they are known as weight functions. They are known as weight functions, or actually they are not functions, they are weights. They are not functions because they are constants. So they are known as weights. And because they are used in quadrature schemes, or numerical integration schemes, they are known as quadrature weights. And let us designate them in general as Wi. Actually, I will Wi. So, in general, my approximate integral can be written as summation of Fi Wi. Actually, I will make it a little better. Fi at node I. So Fi xi means it is the value of f at the ith node, and the coordinate of that ith node is xi, okay, times the quadrature weight associated with that node, and this is being done from 1 to r. So, I am introducing another indice r. So, r is the polynomial order. Actually, it is not r, it is r minus 1. R minus 1 is the polynomial order, xi is the coordinate of quadrature point. So, these nodes in this case these nodes happen to be quadrature points. There is no rule that they have to be same as nodes. We will see later that we will use some different points. Maybe we can use these as quadrature points. But in this case, for trapezoidal rule and Simpsons rules, the nodes are same as the quadrature points. The nodes are same as quadrature point. So xi is coordinate of quadrature point, and fi is value of fx at ith quadrature point. Okay. So, what you have learned today is this terminology known as quadrature, quadrature point, quadrature weights, and what you have seen is that any approximate integral can, if I have a function over a domain, then I can have the integral of that function expressed as, or the quadrature of that function expressed as a summation of a series which is fi times wi, where fi represents the value of f at ith quadrature point and wi represents the weight associated with that point. And if I add these up, then I get my approximate integral, not exact integral. So, this completes the discussion for today. Tomorrow we will continue this discussion and extend this thinking further. Thank you.